Good day, students. Welcome to General Science 101. We are going to continue from where we left off last time. When we left off last time, we were discussing the concept of energy. We said energy basically derives from work. And when we looked at the concept of work, it was force applied and a distance moved. Unless the force and the distance are moved in the same direction, we say useful work is not done. We also at that time discussed the concept of power. Power were basically discussed with you as the total amount of work done divided by the time taken. And the example we quoted was that if I walk up a flight of stairs, let's say about 10 meters, I take about a minute to do so. I'll take a longer time. You might take a shorter time. So my power would be, if I use my weight multiplied by the height, multiplied by 9.81, which is the acceleration due to gravity, divided by 60 seconds, giving me a value which would be my power. We also looked at energy and its different types. We said energy is available in a variety of types. We said there is energy which is available in the nuclear energy, we have solar energy, we have kinetic, we have potential, we have elastic potential energy, we have gravitational potential energy, and so on and so forth. However, for our purposes, we just took two types of energies. We said there are two types of potential energies. There is elastic potential energy and there is gravitational potential energy, because these were the two energies we were interested in, these being part of the mechanics portion of physics. We said that the potential energy is basically due to position in a gravitational field. As I lift something up, it gains energy. In other words, it gains the capacity to do work. Kinetic energy, on the other hand, was energy associated with motion. Anything, any object which has mass and is moving possesses certain energy, because we require to do some work in order to make it stop. And then we discussed with you the law which is overwhelming regarding whenever we are looking at energy, that is the law of conservation of energy, which specifically stated that energy can neither be created nor destroyed. It can only be transformed from one form into another form. When we discussed all of these things, we did say that we are only looking at useful energy. However, sometimes you have to do work. For example, a force which is being applied at an angle will not do the total amount of work which is going to be useful. So we had classified work as useful work, which is in the direction of force, according to the definition. But the other work which we are doing, which is not in the direction of force, is also work which we are doing. We have to do it because that is the way the force is being applied. For example, I'm pushing a lawnmower, I'm pushing at an angle, but the actual work done is in the direction of the force. I want it in this direction, force is being applied this, so some force is going into the ground, some force is going along the surface of the ground, and the force which is along the surface of the ground is the one which we are interested in, and we say that is useful work. The other work which we have done, energy we have expended, is basically lost. From where we said there is a concept of efficiency. Now, system which converts all of our work into useful output is said to be 100% efficient. Efficiency is normally defined as the useful energy output divided by the input, how much energy we put in and how much useful energy we get out. For example, in a motor car, the fuel burnt is the energy which we have put in. That is the amount of energy available. Some of this energy goes out into doing useful work. That means it drives the car, provides the kinetic energy, and the car moves. The unwanted energies, which basically are the exhaust, that is the heat which is given out, it is the friction of the road. This is energy which is not doing any useful work. And therefore we have the system in which a portion of the energy is useful, a portion of the energy is not useful. We are looking at only the portion of the energy which is useful for us. So useful energy divided by total energy we have put in is the efficiency. In the efficiency phase, basically what we are looking at is the useful energy which we require. However, we do have to remember that the law of conservation of energy says that the non-useful energy, which energy is lost, is technically not lost. It is being converted to energy which is not useful for us. It is converted into heat energy, it is converted into overcoming the friction, and therefore it is not useful energy. Now, if we look at the relationship which is efficiency is defined as E useful divided by E input. And if we divide the denominator and the numerator by time, what we get is power, because power is energy over time. So efficiency can also be defined as useful power output divided by the power input, how much power we put into a system and how much useful power we get out of a system. So basically, if you go look at percentage efficiency, then percentage efficiency is useful power output divided by power input multiplied by 100. Now, let's look at a concrete example, a numerical. Let's say a central heating system. Central heating system heating up an environment provides 250 kilojoules of energy in the shape of hot water, which is circulating in the system. So hot water is circulating, is heating up the rooms or heating up whatever you want to heat. It goes back into the burner and it is reheated and reused. It's a central heating system. If the amount of gas which we use as fuel to heat up this water releases 400 kilojoules of energy, we have to calculate the efficiency of the system. Now, in the data, we have two pieces of information. Information A tells us what is the useful input, which in our case was 400 kilojoules. What is the useful output? The useful output, of course, is 250 kilojoules. So total input is 400 kilojoules. The useful output is 250 kilojoules. Formula, of course, which we are going to be using is the formula of efficiency, which says energy output divided by energy input multiplied by 100 is going to give us the efficiency as regard to energy. So efficiency would be 250,000, which is the output energy, useful output energy, which is what the heating system provides, divided by 400,000, which is the energy released by the gas, multiplied by 100, gives us an efficiency of 62.5%. In this case, efficiency is quite high. The efficiency where it is lost, or energy which is lost, is basically when you heat something. Some heat is lost to the surroundings, some heat goes into heating up the pipes, heating up the system, and therefore you have an efficiency which is not 100%. Let's look at another problem. Let us say that there's a boiler which is providing 288 kilojoules of energy, and it provides this in 4 minutes. Now, the boiler is run on an electric power, which is providing 2000 watts of power. So basically, we have an electric boiler, which is providing us 288 kilojoules of energy in the form of hot water. In this case, the data which we have is, we have the power input, we have the power output, and do we have the power output? No, we do not have the power output. We basically have the power input, which is 2000 watts, and power output is not given. However, we are given two pieces of information. We are given the energy available, that is 288 kilojoules. We are given the time taken, which is 4 minutes. So because power is energy divided by time, we get 288,000, which is 288 kilojoules, divided by 240. 240 seconds are the time in 4 minutes, and it gives us a power output of 1200 watts. Once we have this piece of information, that we have the power output, which is a useful, which is about 1200 watts. We have the input power to the system, which is 2000 watts. It's a simple method or a simple step to calculate what is the efficiency of the system. The efficiency of the system would be useful power output, which is 1200 watts, divided by the total power input, which is 2000 watts, multiplied by 100. In this case, it would be around 60%. Now, like we said, in a normal motor car, the fuel is burnt. Now, when the fuel is burnt, you lose quite a lot of energy to the surroundings in the form of exhaust heat, in the form of friction to the ground, and only a small portion is given to the kinetic energy of the car, which is what we are interested in. Now, normally in normal situations, an ordinary domestic car would lose about 65% of its energy in the form of heat or non-useful energy, and therefore the kinetic energy receives only 35%, which is clearly an inefficient use. Because the car is a useful vehicle, it takes people and baggage from one point to another point. Therefore, we accept this usage. We accept this wastage, because that means, as a consequence, we can move from point A to point B very, very effectively. However, it is inefficient. Now, what do we mean by when we say that we have to increase the efficiency of an automobile? On the graph, we are given two cars which are having different efficiencies. The car one, which is on the top end of the slide, is having only 35% being consumed in kinetic energy, and it is losing 65%, whereas the car B is having 45% of its energy being converted into useful kinetic energy, where it is losing only 55% as heat loss. That means car B is going to be more efficient, and hence it is going to have a higher speed. Sometimes in order to increase the speed of the car, we require the efficiency. However, it does compromise on other things. For example, high-speed cars, high-speed vehicles, which you see on the racetracks, have to be highly efficient machines because they have to compete with each other, and the fuel and the weight of the cars, of course, is limited by the racing officials, and the more efficient the car, the faster it will travel, and a small fraction of a energy efficiency will result in an increase in speed, and hence a victory for the driver. Now let us look at another example. Now this is an example of a numerical which is multi-tiered. So it is just one question which will contain a lot of sub-questions. Let us look at, says, you have a figure on the graph which shows a cart of mass 3,400 kilograms being pulled up by a motor. It moves from A to B. When it reaches B, at B it is brought to rest. So in other words, it loses all kinetic energy in this system. So what we are going to say is, from A to B, the only energy which has been provided by the motor, which is pulling this cart up, and the only energy which has gained is potential energy. We have to look at the questions as they are on the slide. They say state the energy changes from A to B. We have to calculate the useful work by the motor. We have to calculate the power of the motor. We are not calculating the efficiency at this point of time because we are not given what the input of the motor is. We have to state the energy changes from B to C, and we have to calculate the speed at D. And now we will go along. Part 7 of it is, we will discuss it slightly later, which says now rocks are added to the cart at B, and we have to ignore friction, and we have to see what would be the speed difference at point D. Let us take it at each step of a time. If we look at the graph, we will find at the diagram which is on the slide, we will see that the point B is 30 meters above the surface from where the cart starts, whereas point D is 12 meters in height. So there is a difference in height and hence a difference in potential energies. Let us start this question step by step. In the first step, we have to see what are the useful energy changes from point A to point B as the cart goes up the hill. When it is at A, we are assuming the cart is at rest, therefore it possesses no energy as such per se, because we are taking that at the ground level. So the motor then provides it energy, it pulls it up to a certain height, and when it reaches B, it has gained a certain height, which is 30 meters. So the useful work done by the motor has been converted into gain in gravitational potential energy. So you have the energy provided by the motor being converted to gravitational potential energy, and that is the energy change that has taken place. We have to calculate the work done by the motor. The work done basically is going to be force into distance. Even though it is going up a slope, the force which we are looking at is the force of gravity. Therefore, we have to look only at the vertical displacement or the vertical height. Now, this means W is equal to mg, or the work done is equal to mgh, which is the gain in potential energy, and it is 3,400 multiplied by 9.81, again multiplied by 30 meters, which is the height, and we get an energy which is about 1,620 joules. And calculating the power output of the motor, total work done by total time taken. The time taken, as stated in the question, it took 15 seconds to go from A to B. Therefore, 1,620 divided by 15 should give you 66.708 watts, or something like 66,708 watts is the power which is required. So it is 66.7 kilowatts power which is going to be provided by the motor to lift this from A to B in 15 seconds. Now, we have to state the energy changes as the cart moves down from B to C and to D. No, B and D are at different heights. C is a dip. So from B point, it had the only energy it possessed was gravitational potential energy. So at point B, the gravitational potential energy at point B was converted to some potential energy at C and some kinetic energy. If you look at the diagram, C is still above the surface. Because it is above the surface, it should still possess some potential energy. Therefore, the first energy conversion we have, gravitational potential energy is converted to kinetic energy at C plus certain gravitational potential energy. Because we do not know the height at C, therefore we cannot for sure say how much gravitational potential energy was there. However, when we move from C to D, some of that gravitational potential energy or some of that kinetic energy is reconverted into gravitational potential energy, and due to inertia it gains a height. But because D is lower than B, therefore it will also have some kinetic energy. Now, next question technically asks us how much kinetic energy and hence what is the speed at D. So to find the speed at D, we have to calculate the gravitational potential energy at D. What is the potential energy of an object which is at a point D, which was at a distance about 18 meters lower? So basically we have at gravitational potential energy at D should be 3400 into 9.81 into 12 meters, which is the height of point D. So the gravitational potential energy at D is mgh, which is 3400 into 9.81 into 12, giving you 400,248 joules. Now we have to calculate the speed at D. Now in order to find the speed at D, we first have to find that component of energy which is going to be converted into speed. The point B had gravitational potential energy. This has gravitational potential energy plus some kinetic energy. So this gravitational potential energy minus this gravitational potential energy will give us energy which has been converted into kinetic energy, and therefore we are going to be looking at the energy transferred. So the energy transferred is going to be basically the initial height energy, which was 3400 into 9.81 into 30, minus this potential energy, which was 3400, that's the mass, into 9.81, which is the acceleration due to gravity, into 12, which is the height at that point, giving us a difference, that is change in energy, is 600,372 joules. So 372 joules, the difference which we get is the energy which is available to us to be converted to kinetic energy. Now, that is what tells us that the kinetic energy is now has gone into the gravitational potential energy and plus the kinetic energy. So change in gravitational potential energy is going to be converted into kinetic energy. Now, the energy which we have available is 600,372 joules. Half mv squared has to be equal to this much. So v squared is equal to twice of 600,372 divided by 3400, which is the mass, giving us 353.16. Or taking the square root of that, we get velocity at this point of 18.79 meters per second. So what we have seen is that by using the relationships of energy, we can get to a certain value which should tell us that this is the speed which is attainable. Now, if we look at the mechanics portion, now this object which was here fell down by a distance of 18 meters. From 30 meters to 12 meters, the difference is about 18 meters. Let us look at the equations of motion which we had discussed way back, that we have an equation which says Vf squared minus Vi squared is equal to 2as. In other words, because we are starting with an initial speed of 0 at B, so how much speed it will gain after it's fallen a distance of 18 meters. So Vf squared minus 0 squared should be 2 into 9.1 into 18, and giving you a value of Vf squared is equal to 353.16, or the final velocity is 18.79 meters per second. If you look carefully, then whether we went the energy route or we went through the equations of motion, which we did in mechanics, you get the same answer, which tells us of the interconvertibility or the compatibility of mechanics with the energy relationships. So you can either use the energy route or you can use the mechanics route and you will receive the same answer. Now, let's go to the final question. This is food for thought. Now, the cart is here. Its weight is 3,400 kg. Now I add some rocks to it. In other words, it becomes heavier. And I let it go. It now falls, and when it reaches D, what is going to happen to its speed? Is it going to be more? Is it going to be same as before? Or is it going to be less than before? Now, looking at it from just the normal perspective, a normal student will say that the speed should increase because the weight has increased. However, if we look at the equations, the mechanics which we have, we get a different answer. The different answer is basically due to the fact that if you look at the equations of motion, Vf squared minus Vi squared is equal to 2As. Mass does not figure in that equation. So basically, the equations of motion are independent of mass. So the force is gravity. Whether I increase the weight or whether I reduce the weight, it is going to have no effect as long as the value of G remains constant. Therefore, whether I add more weight or I add less weight, the speed at the other end would be the same. If we go the energy route, that the potential energy is going to be converted to kinetic energy. Now, potential energy is proportional to mass because potential energy is equal to mgh, G and H being constant, M is the one which is being changed. So as you increase M, potential energy increases as a direct proportion to the mass. Similarly, when we look at the equations of kinetic energy, the kinetic energy is equal to half mv squared. M again is in a direct relationship to the energy. If the mass is increased, the energy has to increase, again in linear proportion. So if we look at it this way, then mass again does not have an effect, and kinetic energy, a change in kinetic energy would be directly proportional to the change in potential energy, and you should get the same answer. So the answer to this question is that when you release an object from B, it moves on to D. Whether we add mass or whether we do not add mass, it is going to be irrelevant. The final speed is going to be the same. In real life, of course, there is going to be some difference. Very simply because when you add weight, the other factors will come into account. Friction might come into account because if a person is sitting there, air drag might come into account. So there would be slight modifications. However, in ideal conditions, the speed would not change. Now, in the two lessons which we have done, we looked at the concept of work, we looked at the concept of power, we looked at the energy and its types. Again, repeating them, we had chemical energy, we had solar energy, nuclear, we had wind energy, tidal energy, and so on and so forth. And we said all of these energies are usable. We looked at the unit of energy and we said it is the same as that of work. In other words, it was joules. We looked at the kinetic energy, we derived the formulas for kinetic energy and derived the formulas for potential energy, and we looked at the law of conservation of energy. And what we have done today is we've looked at the concept of efficiency and how to apply it. And that is basically the crux of the matter, that we have to look at how to apply what different formulas or relationships we have developed in this course. Whatever we have developed has some empirical relationship, and when looking at the relationship, we say, okay, this is what the formula says. If this is what we observe, then this formula is correct. We put it to a test, we get a relationship, and we say, this is the answer. If it is not correct, then we think and we modify the relationship, which is part and parcel of the scientific method. So we conclude this module at over here, and we are now going to continue on with the next module of teaching. In the next module, what we are going to be looking at is basically, we are going to be discussing another type of energy, which is energy which normally is not associated with work. It is heat, and we are going to be looking at a topic which says thermometry. We are going to be looking at the techniques, how you measure the quantity of heat or the hotness or the coldness of an object. Now in this, what we are going to do is we are trying to be explaining to you what is the difference between heat and temperature. We are going to be looking at the fact, how can we use a liquid to define a temperature scale? In other words, we are also going to be looking at temperature scales, how they are defined, how can you identify what is the temperature of an object, when, and so on and so forth. We are going to be looking at what are fixed points and what is meant by two of the fixed points which are normally used in practical thermometry, which is the ice point and the steam point. Why are these identified as such and how we use them? And we are going to be looking at the different parameters which we use in liquid and glass thermometers. Thermometers, by the way, are devices which are used to measure the temperature. Now, when we are looking at the difference between heat and temperature. Temperature, of course, is the reference to whether a body is hot or whether it is cold, with reference to something else. For example, if I put my hand under a tap of water, I will decide whether the water flowing from the tap is cold or whether it is hot, depending upon what the sensation is to my hand. What I'm doing is I'm measuring the temperature. Now, how do I measure the temperature is from the fact that whether the water is losing heat or whether it is gaining heat. So heat basically is being lost by hot water, because when it hits my hand gains that amount of energy. And if it was cold water, my hand is losing energy and the water is gaining energy. So basically, I would feel that water is cold. However, heat refers to the amount of energy that flows from a body. A hot body will lose energy will flow out from hot body. A cold body will absorb energy will flow into a cold body. Now, like we already have said, that when we say a body, what exactly do we mean? Now, body consists of something which has particles. Now, we already know that particles are always in a state of motion. There are some particles which are bound together to each other, and there are particles which can move. Therefore, you have all types of energies in a body. You can have rotational energies. There will be particles which are moving or rotating. There are particles which are vibrating, and there are particles which might even move within a body if it is a liquid. So therefore, all of these bodies will possess some energy. You might have elastic potential energy in case it is vibrating. You might have rotational energy in case it is rotating, or you might have translational energy, which is kinetic energy, in case the particle is moving, or you might have some random energies which we do not know or we have not accounted for. The sum of all these energies is known as the internal energy of the system and is termed as heat of the body. So heat of the body is basically the total energies an object possesses. Now, like we said, heat is energy, and the unit of energy is the joule or Newton meter. Therefore, the unit of heat also has to be a joule or a Newton meter. Now, when we say that heat is, or hotness, temperature is a relative term, what exactly do we mean? Now, if I have my right hand under hot water and my left hand under cold water, and I dip then both of them into normal room water, this hand, because it was under cold water, when I dip into room temperature water, it's going to feel as if this water is warm. However, this hand was under hot water, and when I dip it into normal water, this is going to feel cold. So the same person is going to have two different sensations. That is why we say it is a relative term. And because it is a relative term, we have to devise a method or a technique so that the answer is always absolute. In other words, it becomes a measurable quantity. Like we said, when an object is hot, it gives off heat. It has to lose heat because it has temperature, it has a quantity of heat available, it gives out energy. A cold object, because it has less energy, is going to absorb energy, and energy always has to flow from a higher level to a lower level. Now, in order to define such a system, which is going to tell us what temperature or what is the actual value of the temperature, we have to define it in such a way that something has to lose energy, other has to gain energy. In other words, we are going to define the law of heat exchange. The law of heat exchange basically says a hot body is going to lose energy, and the amount of energy it loses has to be gained up by something, which in this case is the cold body. So heat, like any other energy, flows from a hotter to a lower body. No heat exchange, technically the net heat exchange is of course zero. In other words, the amount of heat lost has to be equal to the amount of heat gained, which is required by the law of conservation of energy. Now, two bodies have to be, which are in thermal equilibrium, cannot have a heat exchange between them. What exactly is thermal equilibrium, we will discuss as we go along into this lesson. Now, when we add heat to a system, what happens to it? Now, there was a system which had particles in it, which were moving around, which were vibrating, which were doing some other things, which we said it had a net internal energy. Therefore, when we add energy to something, it has to A, gain energy, B, it increases its internal energy. That means the rotational, vibrational, or the random energies which are present in that system. It can also appear as work being done on the system. So the system will gain some energy because some work has been done. And it usually results in expansion of matter. In other words, in normal circumstances, when we heat something, it expands. Now, on the other hand, when we take heat out of a system, basically it loses energy. So when we take energy out of a system, the net amount of energy it possesses, it goes down. And as a consequence, the internal energy goes down, or the rotational, translational, or the vibrational energies it possesses become less. And it appears as if the system has done the work, as work done by the system. And it usually results in contraction of materials. Now, whenever we heat something, it expands. This fact has been used in something which is known as a thermometer. Thermometry is the branch of physics which deals with the measurement of temperature. And thermometer is a device which measures temperature. We are going to be discussing with you right now what exactly a thermometer does, how we measure with it, and what are the basic background of thermometers. The SI unit of the thermometry is, of course, the Kelvin. Temperature is measured in Kelvin, which is a base unit. And the symbol of course, it is K, capital K is the symbol which is given to it, and the K does not have a degree to it because it is named after a Lord Kelvin, and therefore the sign small degree, which was in degrees Celsius or degrees Fahrenheit, as you must commonly know, and as we will discuss as we go along, is not there. So let me show you a thermometer. We're going to discuss this as we go along. This is an example of a thermometer, a liquid and glass thermometer, which we're going to be looking at as we continue our discussions. Now, most practical thermometers, like a clinical thermometer and a laboratory thermometer, which I've just shown you, are based on a physical property of solids or liquids that they expand on heating. Now, when they expand, in this case, you have alcohol in this, which is colored red, and as I heat this alcohol is going to rise. What I can do is I can just hold it, and you might be able to see the temperature rise in this thermometer. Now, a thermometer is used for measuring the temperature of objects it is in thermal equilibrium with. Now, we have just stated something which is known as thermal equilibrium. Now, when we say an object is in thermal equilibrium, what exactly do we mean? Now, let us say there are two objects. Can this thermometer in this position measure the temperature of this object? The answer is no, because it is not in contact. In order to measure, I have to bring it in contact. Now, as it is in contact, we will then wait until this temperature or the expansion stops. Once it is stopped, we say this object and the thermometer are in thermal equilibrium. There is no heat exchange between the two, or heat is not being lost by either of the two, and therefore when two objects are in contact and they are at the same temperature, then we say they are in thermal equilibrium. Now, thermometer basically is nothing else. It's a device which measures a physical property of something. There are different physical properties which can be used to create a thermometer, and it does not necessarily have to be linear, but it has to be unique. In other words, one temperature should give only one value of that particular property. For our purposes, we are going to be looking at length. Now, there are different physical properties. If we are looking at a mass of a fixed volume of a fixed mass of liquid, we have the thermometer which I just showed you, which are liquid and glass thermometers. If we're looking at pressure of a fixed mass of gas, we are looking at a constant volume thermometer. If we are looking at resistance of a metal, then the thermometer class would be a resistance thermometer. If we are looking at the voltage being generated by something, we might be looking at a thermocouple thermometer. If we are looking at expansion of metal, you have spiral metallic gauges, which are commonly used in cars. However, there is one type of thermometer which does not require a contact. It is a pyrometer, which technically looks at the wavelengths of light. Now, light which is coming, we record the wavelengths, and from that wavelength, of course, we calculate what should be the temperature of the source. This type of thermometers are used to measure the temperatures of very hot furnaces, or perhaps different stars, looking at galaxies and stars and seeing what the temperature is there. We really cannot go there and have a contact, and therefore we use different techniques. However, we are not going to be looking at that technique. Then in order for this thermometer to work, what we require is a scale. And the second thing which we require is that all of these thermometers, which are made of different materials, which are different in their sense, in their properties. For example, you have a resistance thermometer, a liquid and glass thermometer. They might or might not agree with each other. A resistance of a material might change in a different matter. Their volume might change in a different. However, they should agree at certain points. And in other words, at those points which are known as fixed points, the temperature on all thermometers should be the same. We are going to be discussing this as we go along. We are going to be referring to the three scales which we normally use in everyday life. This is the Celsius or the centigrade scale. We are going to be looking at the Fahrenheit scale, and we are going to be looking, of course, at the absolute scale, which is the Kelvin scale. Now, the two fixed points which we are going to be using are fixed by definition. The 2 points which we are going to be looking at are the steam point. That is, when water is boiling at standard pressure, the temperature is 100 degrees Celsius. The second point is the ice point, that whenever water freezes or ice melts at standard pressure, the temperature is taken to be 0 degrees centigrade. Now, what we do is, we take this thermometer, we first dip it in something which contains a mixture of ice and water at standard pressure. Now, by definition, where this level of mercury should fall or the level of alcohol should fall should represent 0 degrees Celsius. So what we do is, we mark that position and say this is 0 degree on this thermometer. If I'm using some other thermometer, I again dip it into the same mixture and say, all right, on this thermometer, this point is now 0 degrees. This process is known as calibration, and the thermometers have to agree on that point. In other words, no matter which thermometer I use, when I dip it in ice water, it should give a reading which is equal to 0 degrees Celsius. When I take this, dip it into another container in which we have steam coming out, there's special apparatuses available there. So steam at standard pressure, the temperature will rise, and whatever point we get when thermal equilibrium is attained, thermal equilibrium is normally attained when the temperature stops rising. So I say this point, I have marked the second point, which is now going to be 100 degrees Celsius. So 0 degrees and 100 degrees, of course, then it's just a matter of dividing it into 100 equal parts, and I have my divisions which are of 1 degree each. Now, all the thermometers would be accurate only at these 2 points. However, we always assume that their laboratory thermometers which are made or manufactured have a uniform bore, and they are made very, very accurately. So all laboratory thermometers should have normal reading as it is, because if they are agreeing at 0, they're agreeing at 100, and the bore is uniform, then they should agree everywhere along the system, and that is what we are looking at. They're going to be agreeing from 0 to 100 degrees in 1 degree intervals. The precision or the resolution of a thermometer basically just means to what fraction of a degree it is possible to make a reading. For very high temperatures, even if you measure with an accuracy of 10 degrees or perhaps more, it is acceptable, because if you're looking at turbine jet engines which are working at 4200 Celsius, whether you measure 4205 Celsius or 42195 Celsius, it really does not make a difference, and perhaps a thermometer will not be able to give you that smaller reading. However, there are many thermometers which can normally give you a reading of 0.1 degree Celsius. Now, there are certain special thermometers which give up to 1,000th of a degree, 0.001 degree. However, it does not mean that they are accurate. They have to be accurate only if they agree to the other thermometer at the fixed point. The international scale ITP 90, which has been negotiated between different countries, give us a large range of fixed points which can be used in different areas. However, in the laboratory or in everyday life, we use the 2 fixed points between 0 degrees Celsius and 100 degrees Celsius, because all of our everyday work is between this area, and it works in our or normal everyday life. For certain other work, we say reproducibility is important. What do we mean by reproducibility? Let us say that a manufacturer manufactures 100 such thermometers. If all of these thermometers give same reading in similar circumstances, we say this reading is reproducible. And this reproducibility is very important when we are doing work, for example, in school laboratories, so that 40-odd students who are doing that experiment should get more or less the same result. So a variation of plus minus 1 degree is what we expect when 40 students are doing an experiment. They are measuring the temperature of water, for example, room temperature, so the temperature should not vary by more than 1 degree. So some students might get 19 degrees, some students might get 20 and 21, and that would be an acceptable value when we are doing work. So we would say these thermometers are producing a reproducible, and they are consistent with the processes. Now, how does a liquid in glass thermometer work? On the slide, basically what we have is, I've shown you a photograph of a mercury which is in a bulb. It's a very thin glass tube, very thin glass, because we know glass is an insulator, and therefore heat has to be passed through the glass bulb into the mercury, which is going to then expand. There is a very small, thin constriction which restricts the mercury from flowing into the capillary unless it expands or it is forced to go into that. Now, the expanding liquid, when you put this thermometer into some liquid, the bulb is going to be heated up, the liquid inside is going to be heated up, and the level in the mercury is rising. Now, you have a thick glass tube, which is a small capillary in it, and the liquid is forced in the capillary in the thick glass tube. You have a thick glass tube because you do not want that liquid to lose energy and therefore give us a false reading. And of course, when we look at the three scales we have, the three scales have to agree on the ice point and the steam point. So ice point for the Celsius scale is 0 degrees Celsius. For the Kelvin scale, it is 273 Kelvin. For the Fahrenheit scale, it is minus 32 degrees Fahrenheit. Whereas the steam point for the Celsius scale is 100 degrees C. For the Kelvin scale, it is 373 Kelvin. And for the Fahrenheit scale, it is 212 degrees Fahrenheit. The scales were developed in different times through different requirements. The earlier scale, of course, was the Fahrenheit. Then, of course, Celsius developed the centigrade scale, which is more practical and more common because it breaks up the divisions into 100, which is more manageable and more understandable. Now, if we look at the difference, on the Celsius scale, the scale is between 0 and 100. There are a total of 100 divisions. In the Kelvin scale, the ice point and the steam point have again 100 difference between them. 373 minus 273 gives us a difference of 100 Kelvin. That means 100 degrees Celsius change is equivalent to 100 degrees Kelvin scale, or 1 degree Celsius is equal to 1 degree Kelvin. And the conversion between these two is going to be quite convenient. However, when we look at the Fahrenheit scale takes the steam point at 212 degrees Fahrenheit, whereas the ice point is minus 32 degrees Fahrenheit. Now, if we look at it carefully, it goes below 0 and it comes to as minus 32 F. 0 is slightly above in this case. So we have a difference of 180 degrees Fahrenheit between the ice point and the steam point. Now, the diagram which is on your slide basically shows how a thermometer works. You have the 2 points, which are the ice point, which represents the length naught, because if you look at our thermometer, even at 0 degrees centigrade, you might have a certain length which has been covered by the liquid because it is expanding. So you have L naught as the ice point, and the second distance, which is L100, which is the steam point. Unknown temperature might be at this point X. A change of property, in this case length, corresponds to 1 degree Celsius. 1/100th of the distance between L0 and L100, 1/100th of this is going to correspond to 1 degree. It is the same as 1 degree Kelvin. Now, if we plot it on a graph, we are assuming that the property is changing continuously between the ice point and the steam point. So we would have a straight line on the graph. So between the ice point and the steam point, or between L0 and L100, you are going to get a straight line, and Lx is basically the temperature which I am going to measure. So I have this thermometer connected to some unknown object, and it is measuring the temperature. Basically, what I'm looking is the distance Lx. Now, the relationship, of course, would be using a ratio method, Lx minus L0 divided by the length at 100 minus the length at 0 into 100, giving me our Celsius measurements. Let us do a numerical to more reinforce what I have said. Let us say that in an unmarked thermometer, it was found that the ice point was at 5 centimeters. So the point 0, which I'm saying is 5 centimeters from the end. And the steam point is 25 centimeters from the end. Now we have to find the unknown temperatures at 2 points. One, when the length from 0 to this point was 14 centimeters, and the second, when it was only 3 centimeters. So we have a data which is available. That the data states that we have L0 is equal to 5 centimeters, L100 is equal to 25 centimeters, Lx1 is 14 centimeters, Lx2 is 3 centimeters. We have a relationship we just developed, that Lx minus L0 divided by L100 minus L0 multiplied by 100 should be equal to the temperature I'm looking at. So for 14 centimeters, it is 14 minus 5 divided by 25 minus 5 into 100, giving me a temperature of 45 degrees, whereas for 3 centimeters, it is 3 minus 5 divided by 25 minus 5 into 100, giving me minus 10 degrees centigrade. In other words, the temperature when it was 14 centimeters is 45 degrees, and when it is just 3 centimeters is 10 degrees Celsius. Now, when we're looking at the 3 scales of temperature, we have to look at a general relationship for the 3 scales of temperature, or for any scale which we have. And the general relationship basically is you have equation on the left-hand side and on the right-hand side. On the left-hand side, on the denominator, you have temperature on scale A minus the ice point on scale A divided by the number of divisions on scale A. On the right-hand side, you will have temperature on scale B minus the ice point on scale B divided by the number of divisions on scale B. Basically, what we are doing is we are comparing 2 scales. Let us look at the fact of interconversion from Fahrenheit to Celsius. Now, Fahrenheit, temperature C on the Celsius scale minus the ice point of the Celsius scale is of course 0. We divide this by 100, whereas in Fahrenheit, the temperature F minus 32, which is the ice point, divided by 180. So Tc should be 100 over 180 into Tf minus 32, giving us Tc is equal to 5 over 9 multiplied by Tf minus 32, or Tf is equal to 9 over 5 into Tc plus 32. You can get the same relationship of conversion from Kelvin to Fahrenheit. However, in this case, Kelvin, the ice point is 273 degrees. So Tk minus 273 divided by 100, because we're looking at a difference of 100, is going to be Tf minus 32 over 180, and giving you a relationship that Tk is equal to 5 over 9 Tf minus 32 plus 273, where the temperature in the Fahrenheit would be 9 by 5 multiplied by Tk minus 273 plus 32. And for Celsius to Kelvin, of course, we have to just add 273 to the Celsius temperature to get the Kelvin temperature, and we have to subtract 273 to get the Celsius temperature, and so on. When we meet in the next lesson, what we are going to do is we are going to look at these relationships and try to use them in numerical problems to get to see how you can convert from one scale of temperature to another temperature scale. So what we have done in this lesson is, with you, we have looked at what is the difference between heat and temperature. We have said heat is the amount of energy a body possesses, and when an object loses heat, it loses energy. When an object gains heat, it gains energy. We have also looked at what is temperature. We said temperature is the degree of hotness. And because a human body is not very good at measuring temperature, when I have my hand under hot water and I dip it under normal water, my hand is going to feel cold. When I have it under cold water and I dip it into normal water, this is going to feel hot. Therefore, I am not a good judge of temperature. Similarly, I can touch two different materials. I can touch a metallic material and I can touch a wooden material, and I will feel them differently even though they are at the same temperature. So we required something to measure it, and that is why where a thermometer came in, and we are going to discuss it as we go along into the next lesson. Thank you very much.